right, welcome to lesson 8.3, the one that you might be looking for but can't find it, like that lone Easter egg you can't find. It's because I think I made the video and it was blurry and really bad, and so I had to delete it. And so I made a new one. I'm making a new one right now and giving it to you. And it's one of the biggest ones in this chapter, next to limiting reactants, going from mass to mass. But this is how to do conversion factors, going from mass to mass conversion factors, not just simply mole to mole conversion factors. And so it can be a little bit tricky. So here you go. We're on 8.3. We're doing conversion factors. We're using the chemical equation as a recipe to do chemical conversion factors. All right, we're still using the chemical equation as a recipe, but that chemical equation is in terms of moles. That recipe is in terms of moles. So everyday life, you're going to be dealing with gram measurements. And so you're going to need to be able to still use the recipe and make mole to mole conversions, but yet you're going to need to be able to start in grams and get to mole of one substance and then convert between that substance and another substance in terms of moles. But then when you're all done, you're going to need to get back to grams. So you're going to need to get out of moles and get back to grams. So moles is kind of like an intersection where we can do a lot of math. We can analyze our chemical equation. We can analyze our recipe, analyze relationships. Again, all that's called stoichiometry. It's a fancy word for analyzing recipes. And let me show you a better angle maybe here. And I have this picture in the PowerPoint, so you can look at it there, or you can just see it in the video too. I'll upload it, and you can hopefully copy this down in your notes. This is a really nice map. This is a really nice map of how to get from one unit to the next. All right. So I encourage you to jot that down in your notes if you need it. But you know, if you understand conversion factors, you don't need this. This is for getting started. Okay. So I don't want to waste too much time. I want these videos to be quick, and I'm going to try not to ramble, because I know you can always pause this. You can always rewind it. You can always restart it. And so I'm just going to jump right in, not without maybe adding this picture really quick to my PowerPoint, because I just actually took that now. So, okay. So here we are. Let's just do a quick recap, actually, too, of where we started out. You know, when we analyzed this pancake recipe, we kind of use it as an analogy, and then we said, okay, well, instead of making pancakes, we can make molecules, right? We can make molecules, and we can look at chemical equations like this: hydrogen gas and nitrogen gas coming together to make ammonia in these very specific recipes. And we can, if we know how many moles of hydrogen gas we have and how many moles of nitrogen gas we have, we can easily tell how much ammonia we're going to make, or we can tell how much nitrogen gas is going to react with the certain amount of hydrogen gas. You can analyze any relationship, a reactant to reactant relationship, a reactant to product relationship, even a product to product relationship. Essentially, if you have two products, a lot of chemical equations have two products. So okay, then moving on. Here we are. We already did the mole to mole 8.3. We're in 8.4, and so I wrote that down wrong. I'm sorry. I'll need to change that. We're doing 8.4. Excuse me. I already gave you 8.1 to 8.3. This is 8.4. And so making molecules, mass to mass conversions. This little blue box to yellow box to yellow box, and then yellow box to blue box is essentially the map I have. So that little solution map there is essentially the same thing as this. All right, but I kind of like how they have the mole boxes, mine are circles, moles of A to moles of B. They have those in a different color. So what that signifies, or what that really emphasizes, is that there is where you can actually analyze the ratio from your balanced chemical equation. And your equation's got to be balanced, otherwise your recipe's wrong. If your chemical equation is balanced, you can analyze that thing, and you can figure out how much of one substance will make of another, or how much one substance will react with another. It depends on what relationship you want to analyze. But the point is, you can figure out how much of one substance is related to another substance altogether. Okay, going from a blue box to a yellow box is just simply using the molar mass to go from grams to moles. That's it. All right. Or going from a yellow box to a blue box is just the opposite. It's going from moles back to grams. Still using molar mass, just using it upside down, if you will. There's no such thing as right side up or upside down. It's molar mass is what it is. It's just a ratio of how much a substance weighs in grams if you have 1 mole of it. So let's do some of these problems. They're just kind of lengthy. That's all. Students kind of get lost in them. That's really all that really happens here. So yeah, I can't really show you this image because it's technically 8.4, but that's just that's the picture I just took of the one on my wall. This is the one I drew the other day of the video I had to erase. But okay, I'm not going to read this controversy over oxygenated fuels, but that is an interesting read if you want to read that. It's something kind of interesting. But I do want to go back to this screen here underneath this solution map. They give us a recipe. They give us one of my favorite recipes here. 2 moles of C8H18. What do you think that is? That's octane. Notice the L for liquid. So liquid octane, because it's got 8 carbons, like an octopus has 8 legs. 2 moles of octane will come together with 25 moles of oxygen gas to produce 16 moles of carbon dioxide gas and 18 moles of water. That's a big equation, right? Could we reduce that down? Could we reduce those numbers down equally by the same amount? No, we can't. We can't really cut anything. We could cut all the numbers in half except that 25. If we cut that in half, we'd end up with like half a molecule, and that just doesn't make sense. So we need whole numbers as those coefficients, remember? So I'm down here at the bottom looking at this recipe. We always need whole numbers. So we're dealing with large quantities. There's going to be some relationships there that we could analyze. So, like for example, we could analyze how much carbon dioxide we would produce in terms of global warming, because that's actually how the chapter opened up, was about this graph of how global temperatures are rising, because you literally produce a lot of carbon dioxide when you burn just 2 moles of octane. And so here we are. Oh, I'm sorry, the problem was still actually on the other page. I skipped it. I looked straight at the recipe, but it says here, suppose we want to calculate, literally what I just said, the mass of carbon dioxide emitted upon the combustion of 5.0 times 10 to the 2 grams of pure octane. I love how they do that. 5.0 times 10 to the 2 grams. How much is that? Times 10 to the 2. That means move the decimal 2 places. So if you do that, what do you end up with? 500 grams. Not even a kilogram. Actually, exactly half a kilogram. Because 500 is half of 1,000. There's 1,000 grams in a kilogram. So half of a kilogram of octane, not even that much. But that's kind of the point of this problem, though, is they're literally saying, hey, if you don't even have half, if you don't even have a whole kilogram, you have half of a kilogram of octane. How much carbon dioxide would you make? That's an interesting proposal. How much carbon dioxide would you make? Well, you want to start with what you know. We do know that we're starting with 5.0 times 10 to the 2 grams of octane. And what we're going to want to do is we're going to want to go from the bigger picture. Here's the bigger picture, okay? We're essentially going to want to go from octane to CO2. All right, that's our map. Our map needs to get us from octane to CO2. There's got to be a relationship between octane and CO2. And there is. I mean, you look at the recipe, we can see it there on that other page. There's a recipe that has that relationship. It's 2 moles of octane will make 16 moles of CO2. You see it there at the bottom? So it's about an 8-to-1 ratio, right? It's an 8-to-1 ratio. You get about 8 times as much carbon dioxide as you do octane. But here's a good question. So let's face me for a second. Here's a good question. It's an 8-to-1 ratio. One molecule of octane, 8 molecules of carbon dioxide. So it's a lot. Every molecule of octane is going to produce 8 molecules of CO2. So then can't we just look at that number in grams and say multiply it by 8? It's just 8 times more? No, not in terms of grams. It's 8 times as much in terms as like if you were to like literally count the molecules. Okay, but those molecules weigh different. In fact, octane weighs a lot. So octane is going to weigh a lot, but those CO2 molecules, they're not going to weigh as much. But we're going to be given numbers in grams that we need to turn to moles so that we can look at that 8-to-1 or 16-to-2, however you want to say it, relationship. So here you go. They have a solution map there here you go. You can see you have a solution map there that goes from the purple box to the green box to the yellow box to the red box. And all they did was put the units there just to say, hey, we need to go from grams of octane to moles of octane, and then moles of octane to moles of CO2, and then from moles of CO2 to grams of CO2. And then to go from grams to moles of a substance, you're using molar mass. Like you can see there, it's 114.3. They've done the dirty work for us. I love it. It's 114.3 grams per mole. That's the molar mass of octane. You won't find that on the periodic table, but you will find the molar masses of the elements on the periodic table. And if you add up the elements in that compound, you'll see that it's 114.3. And so that relationship right there will get us from grams to moles. Okay, then that's 16.2, that 16.2 you can see there in the middle, that'll get us from octane to CO2. And we're essentially there. We know how much CO2 now. If we stopped there, we'd have a unit in moles of CO2, but it'd be better to have it in grams of CO2. So that's why going from the yellow box to red box is simply using molar mass again. And this time you're going from moles of CO2 to grams of CO2, which I think I've got that one memorized now too. It's 44 or 44.01 sig figs, depending on what periodic table you're looking at. So basically, we're going to be using those conversion factors. And let's just go straight to the solution here. We start with what we know, which is 500 grams or 5.0 times 10 to the 2 grams of octane. I would normally put that over 1 just so I know that's on the numerator. And then they make a conversion factor that immediately turns that into moles of octane. So the 114 grams of octane on the bottom and 1 mole of octane on top. And then they make the next conversion factor, putting the unit down first, moles of octane that you want to get rid of, and then putting the unit you want to go to next is moles of CO2. And the relationship is you have 2 moles of octane for every 16 moles of CO2. And then, again, you could stop there and you would know how much CO2 you have, but it's better to know it in grams. So we want to put moles of CO2 on the bottom and grams of CO2 on top of that conversion factor that's last there. And it's 44.01 grams of CO2 for every 1 mole of CO2. Crunching the numbers finally gives you 1.5 times 10 to the third, which is really just 1,500. 1,500 grams of CO2 is your only unit left after you've had the joy and privilege of canceling all those units. So 1,500 grams of CO2. So we have, what did it say, 500 grams of octane? So 500 grams of octane. Well, that's only going to be about a pound or so. This is very little, right? Maybe half a gallon or so of, not even that maybe, of octane. Not that much. It's literally going to produce 1,500 grams of CO2. 1,500 grams of CO2. And that doesn't weigh a lot. CO2 doesn't weigh a lot because it's not very dense. And so if you were to think about how much space 1,500 grams of CO2 would occupy, it would be a lot. It would be a lot of space. Okay, so that's why all these cars running around burning octane, they're producing a lot of CO2, and it's just filling up our atmosphere, and it's a good greenhouse gas. So it definitely contributes to some of the greenhouse effect of the global of the globe, of the Earth, and so that could contribute and has to the rising temperatures. And then, of course, those can have devastating effects if you look at ecosystems and stuff. So, all right, back to the lesson here. Mass-to-mass conversions. Let's look at another chemical equation. I love that this one is part of my next favorite subject, biology. So you guys remember me from last year. I was just fascinated with this. I think it's just so awesome how God designed plants to take CO2, the stuff we just talked about in the air. They can take CO2 from the air, water from the ground, and they can make oxygen and sugar. They can make sugar for us to eat. So I love that. That's so cool. That's such like the circle of life, because then we eat sugar and breathe in oxygen and make CO2 and water. That's cellular respiration. So photosynthesis and cellular respiration are a beautiful cycle that is created by God to move materials around the earth and not only power us, but allow plants to thrive and take CO2 out of the atmosphere. And so really cool stuff here. And let's read this equation. Let's read this in terms of a recipe. It says that 6 moles of CO2 gas react with 6 moles of water, and in the presence of sunlight and a chloroplast doing all the work on the electron transport chain and all that, it ends up producing 6 moles of oxygen gas and just 1 mole of glucose, C6H12O6. How many grams of glucose, though? How many grams of glucose could you weigh on a scale? Or how much of it could be synthesized or produced, however you want to say it, from 58.5 grams of CO2? 58.5 grams of CO2. Now, the last problem we just did, we discovered that that half a kilogram of gasoline would make 1,500 grams of CO2. Here we want to know, just taking 58.5 grams of that CO2, how much sugar would we get out of that? Like, how many grams of glucose would the plant be able to make? And so, of course, we have to assume that there's plenty enough water to go around, obviously. So we're throwing that curveball in there. If you've watched 8.5 and 8.6 videos, you know what I mean by that. In this case, we're not talking about a limiting reactant here. We are actually we are. This would be a limiting reactant. It's the water that's not going to be a limiting reactant. The water's not going to limit us in any way. We have plenty of water. We have excess water. We are going to completely use up all this CO2. If we completely use it up, then what would happen? How much glucose would we make? So just simply convert that. Take that 58.5 grams of CO2, run it through a series of conversion factors you see there, and take it to moles of CO2, then take it to moles of glucose, and then take that to grams of glucose. And there's the conversion factors right there, beautifully produced for you. If you don't know how to come up with those conversion factors, refresh, watch a tutorial, or Zoom me on Google Classroom. Tell me you want to do a Zoom meeting, and I can show you how to add up the molar masses of elements within a compound to find the molar mass of a compound. It's quite simple. So 2 of those conversion factors, the first one and the last one, are just molar masses going from grams to moles. That middle one is what it's all about. That middle one's the magical one, because it takes us from moles of one substance to moles of another substance, right? So going back to this picture here, the beauty is all right here at the top. Going from A to B. That's pretty cool that you can start knowing how much of one substance will be related to the other. Going from grams of A to moles of A, you're just simply changing your unit, but you're still talking about A. Going from grams of B to moles of B, or moles to B to grams of B, you're just simply going back and forth between how much B you have. But going from A to B, that's special, and you need a chemical equation to do those conversion factors. There's no other way to just make those up. All right, so you have to have a recipe that tells you how much of A is related to how much of B. Okay, and so be happy when you have your chemical equations. There might be some problems I don't give you that chemical equation though, so keep that in mind. You have to balance your own chemical equation and get your own recipe. You guys know how to do that. You've balanced equations before, all right? Especially this one, photosynthesis. I would sure hope you know how to balance that. I think I told you the trick to that one. Students hate balancing equations, so it's like the mark of the beast, so you just add 666 there to all those compounds. Anyways, let's look at the solution now. Every time I back out, it makes me want to move that picture. Here you go. On the next page, at the top there, you can see they take 58.5 grams of CO2, convert it to moles of CO2, and then the next conversion factor goes from moles of CO2 to moles of glucose, this special conversion factor there. And then we go from moles of glucose to grams of glucose. Look at all the units canceling. That's kind of rewarding and satisfying to look at. And then make sure you multiply all your numerators across, all your denominators across, and then do your division. So you got to be careful not to, well, you don't have any addition or subtraction, so you should be all right. You could actually just do 1 divided by the next one, multiplied by the next, and then, but if something's on the bottom, it means divide. If something's on the top, it means multiply. And you get 39.9 grams. So there's our conclusion. There's our results. So we didn't start out with a whole lot of carbon dioxide to begin with. We said, what, 58 grams? That's not that much. And so it's only going to make 40 grams of glucose. But that's actually a considerable amount. If you were to put 40 grams of sugar on one of your scales in the lab, you'd see that it occupies a pretty good amount of space. Okay, so there's a Skill Builder 8.2 there with the answer in the back at the end of the chapter if you want to practice that one just to see how you know what you're doing. Those are good problems. I like to grab those for the test usually because I know you guys don't usually do those. So if I don't do them in class and I need a quick equation to do, I usually steal the Skill Builders or the Skill Builder Plus, or I'll take an even that maybe someone copied in the back. So keep your eye out. Do all the work in here. Do it yourself, because if you're exposed to these problems, I'm sure you'll see it again. A lot of these compounds are repetitive, and equations can be repetitive. And so there you have 31, 32, 33, and 34 will be helpful mass-to-mass conversion problems to do. Remember only to do the ones that I assigned you. I'm reducing your workload, but that's related to what I just said. Make sure you're doing the work, not copying from the back of the book and then just getting the answers down for my sake, because you'll struggle on the test, which could be timed, or in a Google form, so that there's a little more pressure. I know the last one I just made an open book because it was just too much, and I know you guys were stressed, but this time be prepared to take a test, even at home, in some kind of environment where you're not allowed to use to just scroll through your textbook. At least you're going to obviously have the periodic table and all your tools that are necessary, maybe even this cheat sheet that's like up on the wall. So if you want to use that, but that's kind of a crutch. You really should be able to do this without that. Let's do this next one, and then I want to be done with this video. And you could actually leave this video now if you understand this. This next example literally just adds, well, it adds 2 more steps, but just really 1 step on the front end of the problem and the back end of the problem. And basically all that is going from kilograms to grams. So, you know, yes, you might get one like that on the test, just to make sure you guys know how to go from kilograms to grams. Because molar masses are not in terms of grams, and if I give you a kilogram number, well, then you're going to have to convert it to grams, because molar masses are in terms of grams. And you're using the molar mass to get to moles, right? To go from the blue box to the green box. And then the green box to the yellow box is just simply mole to mole. You know how to do that. The yellow box to the orange box is molar mass as well, to get from moles to grams. But if I wanted to know an answer in kilograms, going from the orange box to the red box, you would need to know that there's 1,000 grams in 1 kilogram. And yes, that's something I would need you to know. I want you to memorize that by now. Every middle school student should have the fact that 1 kilogram is 1,000 grams, right? And 1 gram is 1,000 milligrams, right? Those are basic everyday units. Okay, so I'm not necessarily going to work that one out, but let's read the problem first. One of the components of acid rain is nitric acid, which forms when nitrogen dioxide, which is a pollutant, reacts with oxygen and rainwater to form the following compound, HNO3. Remember when you have H in front of a compound, that makes it an acid? So H with nitrate, what does that make? Nitric acid. Remember I ate something icky? I ate something icky, Sprite is delicious, and my ride has hydraulics. That was the mnemonic for memorizing how to name acids. Well, we have nitrate there as the product. We have nitrate coming together with hydrogen. And so that's an acid. And we say, since it's nitrate, we say nitric. Okay? And so look here, this is an interesting equation. Let's read it. 4 moles of nitrogen dioxide gas come together with 1 mole of oxygen gas, and also come together with 2 moles of water to make 4 moles of nitric acid. So in this equation, we actually have 3 reactants and only 1 product. So it's kind of a cool equation. And it says, assuming there is more than enough oxygen and water, how much nitric acid would be made in kilograms? So how much of that nitric acid in kilograms forms from 1.5 times 10 to the 3? Oh, goodness, why do they all... I know why they do it. It's because sig figs. There's only 2 sig figs in that number, but 1.5 times 10 to the third is just 1,500 kilograms. So if we have 1,500 kilograms of NO2, that pollutant, how much nitric acid would we make? So first convert the, let's go straight to the solution over here. First convert the 1,500 kilograms of NO2 to grams of NO2 by using that conversion factor there that you see, the first one that with kg on the bottom and g on top. All right, that gets out of kilograms and gets us into grams. Okay, then we can make that conversion factor that has grams on the bottom and moles on top. And then now that we're in moles, we can use the recipe. And it's really a 4-to-4 ratio. You see that conversion factor there? It's a 4-to-4 ratio, which is really the same thing as 1-to-1. So basically, what this recipe says that for every NO2, you're going to get 1 HNO3. Now that doesn't mean for every 1 gram of NO2, you're going to get 1 gram of HNO3. No, because they each have different molar masses. What this recipe says, since it's in terms of moles, is that for every 1 molecule of NO2, you're going to get 1 molecule of HNO3. All right, so it's 4-to-4, 1-to-1, same thing. 4-to-4 reduces down to 1-to-1, or simplifies down to 1-to-1. So, but all these other numbers and units in our conversion factors here are going to help us out, because the molar mass of nitric acid is 63.02, whereas the molar mass of NO2 is 46.01. And so by the time you crunch all those numbers, you're going to get not the same number. You're going to get 2.1 times 10 to the third, which is 2,100 kilograms of nitric acid. So you get a whole lot more nitric acid than you started with the NO2, even though it's a 1-to-1 ratio in terms of the recipe. So it's not always super intuitive, especially with the mass to mass. Here's another Skill Builder 3. I would look to work on that one. That's a cool example too of another acid type of acid rain, in this case sulfuric acid. So if it's NO2, you're going to make nitric acid. If it's SO2 gas in the air, it's going to come together with the same ingredients, oxygen and water, to make H2SO4, sulfuric acid. So there you go. Climate change and acidic rain all in one lesson. Good stuff. And speaking of combustion, did you guys see my my go-kart engine there? I'm going to end up rebuilding that motor by the time school's out. And one day I'm going to make a lesson or a video tutorial explaining the internal combustion engine there and how that piston moves up and down and compresses gas and air. So hopefully we can consolidate some of the concepts we've learned with gas laws and combustion, and you guys can understand how car engines work, because a one-cylinder motor is the same concept as an 8-cylinder motor. Hopefully none of you guys are driving around with 8 cylinders yet. Your first car should be a 4-cylinder. No, kidding. It's good to have an 8-cylinder, powerful car. Keeps you safe on the road. Get a truck, by the way, so you can move your stuff when you graduate, and you can move your couches to your dorm and all that stuff. And trucks are valuable. Cool, man. I'm excited. Don't be overwhelmed when you get all these videos at once, because you have plenty of time to watch them. I'm just giving them all to you so you have plenty of time to schedule them and watch them in your own time, because you're all managing your own schedules in different ways. And so at the same token, don't be offended if you don't see anything for a little while. You may get caught up and be like, well, Mr. Hans is not doing anything, but I just got set up to where I could do these quicker, and I'm giving them to you now so you can spread them out manage your time. Remember, it's May 1 that we're looking at to test on this chapter. As we get a little closer, I'll get you a practice test. Not the day before. I'll give you extra time to work on that practice test, since some of you may be, again, you all have different schedules. Some of you may even be going on vacations when you're not supposed to, but don't feel bad. I did. I went to the poppy fields. Well, that was like 2 weekends ago. I heard today, like, they don't even want you out. They're even giving tickets at the beach. Well, that's where it started, but now I heard a rumor they're even giving tickets if you're not wearing a mask, like in San Bernardino County. And so it's getting a little steeper and steeper. My pastor even told me, though, that this weekend, he said they're not even doing church inside, like, because we had people filming. I work in the media, not work, but I volunteer in the media, and sometimes I help out with that. And he was saying none of us can even go there and do that and film the pastor inside the church. They said no church meetings. Like, well, that's getting a little intense. Not that I'm worried. I'm not afraid of government infiltrating the church services, at least not yet. This is obviously, this is obviously a legit reason, we have a reason to stay home. But you can suspect all the YouTube videos that are be coming out, like, the government is telling us we can't worship, all this. Like, oh. All right. Good talking to you guys. Wish you could talk back to me. Join my Zoom sometimes just to say hi and show your face. And then, all right, we'll see you.